All right, today we are diving headfirst into the seriously weird world of quantum computing. We're going to see how it can solve certain kinds of problems with a speed that is just unbelievable. Our mission? To crack a secret code using a method that seems to break all the classical rules. Let's get right into it. So, picture this. You've got a mysterious black box. You can feed it a string of ones and zeros, and it spits back a single answer, a 1 or a 0. That's it. Now, inside this box, there's a secret binary code. Your job is to figure out that entire secret code. But here's the catch. You have to do it by asking the fewest questions possible.
Now, this little puzzle actually has a pretty formal name. It's called the Bernstein-Vazirani problem. And it's a classic for a reason. It's basically the perfect way to show off the raw power and, the completely different way of thinking that quantum computers bring to the table.
Okay, so what is actually going on inside that box? Well, it's running a pretty simple function. Don't let the math scare you. It basically takes your input string, x, smashes it together with the secret string, s, that's the dot product part, and then it just tells you if the result is even or odd. But honestly, all you really need to remember is that s is the secret code we are hunting for.
First up, how would a regular computer, what we call a classical computer, try to solve this? Well, it would have to be super methodical, very logical, and, you'll see, kind of slow.
So, to find a 4-bit secret code, a classical computer has to ask 4 different questions. First, it sends in 1, 0, 0, 0, just to see what the first bit of the secret is. Then, it sends 0, 100 to check the second bit. Then, 0, 0, 1, 0 for the third, and so on. It has to go through and check every single bit one by one.
And this is where you see the classical limitation, right? If the secret code S is n bits long, you have to ask the box exactly n questions. There is no shortcut. If the code is 100 bits long, that's 100 questions. 1,000,000 bits, you guessed it, 1,000,000 questions.
But what if I told you there's another way? A way to ask just one super clever question that reveals the entire code all at once. Yeah, that's where we take a quantum leap. And here it is. This is the mind-blowing difference. Classically, you need n questions. With a quantum computer, you need just one. Not one per bit. One question. Total. No matter how long that secret code is. Seriously, let that sink in for a second.
So, how on earth is that even possible? Well, it all comes down to 2 of these really wild quantum principles. First, you've got quantum parallelism. The best way to think about it is like trying every single key on a giant keychain on a lock at the exact same time. And second, there's quantum interference. This is this amazing trick where all the wrong answers are basically programmed to cancel each other out, kind of like ripples in a pond, leaving behind only the one right answer for us to see.
So let's peek inside the quantum circuit for a minute to see how this whole thing is built. We're not going to get lost in the weeds here, I promise, but let's just look at the high-level strategy that the quantum computer is using.
The whole process happens in about 5 stages. First, we get our quantum bits, our qubits, all ready to go. Then, we put them all into superposition, and that's the magic step where they explore all the possibilities simultaneously. Then, we query the black box, which has a cool name in quantum language, the oracle. After that, there's a crucial step where we use that interference I mentioned to make all the wrong answers vanish. And finally, we just measure the qubits, and the secret code, well, it just appears.
Okay, theory is awesome, but let's actually see this thing in action. It is time for the grand reveal. Let's run a real example through this quantum algorithm.
So let's pretend the secret string that's been hiding in our black box this whole time is 1101. Now remember, a classical computer would need 4 questions to figure this out. The quantum computer, on the other hand, after running through its 5 steps, gets the full, complete answer in
1. A single query. 1 question to that oracle, and it learns everything it needs to know. That right there is the heart of the quantum advantage for this kind of problem.
So what does it see when it finally measures those qubits at the end? It sees the string 1101, the exact hidden string, revealed completely. No guesswork, no painful process of elimination, just the answer.
Now this is way more than just a clever party trick. This ability to pull out a hidden structure in a single go, it has some pretty profound implications for solving some really tough real-world problems.
So what's the big takeaway here?
It's that for certain types of problems, especially problems that are all about finding a hidden structure or a pattern, quantum computing isn't just a little bit faster, it is playing a completely different game. It takes a problem that gets harder and harder the bigger it is for a normal computer and just solves it in one clean, elegant step.
And why does this actually matter?
Well, imagine trying to find a hidden pattern buried in a massive data set, maybe in finance or biology. An algorithm like this gives us a powerful new tool for that exact kind of discovery, and it can do it with a speed we've never seen before.
And that kind of leaves us with a really fascinating question to think about, doesn't it? The Bernstein-Vazirani problem reveals a hidden string. But as this technology grows and matures, what other, way more complex secrets hidden in science and medicine and all of our data, what could a single, well-crafted quantum query unlock for us next?